Let's consider a particular problem. This is from the Osborne and Rubinstein text, question 2 in chapter 3. It says, a parent has two children, A and B. So here's the parent, and here's her two children, A and B. The parent has in hand only one gift. The parent is indifferent, that is, they see it just as good to give the gift to A or to give the gift to B. But they prefer, over either of those options, they prefer to toss a fair coin, to flip a coin, and if it's heads, give it to one, and if it's tails, give it to the other. The question asks you, so this seems reasonable that the parent should have preferences over these three really choice procedures. The question then asks you to explain why the parent's preferences are not consistent with expected utility. Okay, so I will go over a way you might explain it, but then I will say, well, actually the way that they phrased this may not be completely consistent with the way that it's formalized in the suggested answer, which I'll give you in just a moment. Okay, so how do we express these things, these preferences, formally? Well, this is an actual procedure, giving the gift to A, giving the gift to B, or tossing a fair coin. But let's just, for now, in the simplification, think about the outcome of these procedures. Okay, so give gift to A, then child A gets the gift with certainty. Okay, so we'll call that outcome just simply A, and I put brackets around it because this is consistent with the notation that this is a probability 1 event. Okay, the next possibility is give gift to B. We'll just call that B with brackets around it. Okay, so what's been stated is that they're indifferent between either of these. So we can state that according to their preference relation, they're indifferent, as in A is seen as just as valuable as B. Okay, then finally, what about this third option? Again, toss a fair coin. Half the time gift goes to A, half the time it goes to B. Well, we can just think about the probabilistic outcome of that. So we think of it as a lottery. And using the notation, we write this as, what's the probability in this lottery of the gift going to A? Well, that's probability 1/2, or 0.5. So we say 1/2, use this dot to say with probability 1/2, we have the outcome A. And then when we say, and with another probability, we use this symbol. So we say, and with some other probability, in fact, the remaining probability 1/2, we have outcome B. In other words, the second child gains the gift. So dot B. Okay, and it's been stated that this is preferred to either this or this. So we can write 1/2 A and add the half probability of A, and add the half probability of B and a half probability of B. Sorry, I'm having pen issues here. Half probability of A and half, that's better, half probability of B is strictly preferred, right? Because it says they prefer this, strictly preferred to A. You could also write it strictly preferred to B because they're indifferent between A and B. Okay, so we have three different preference relations or really two, but however you want to say it, that have been expressed. These two things, that these are indifferent, and this is preferred to either of those. The question is set, so if these were the preferences, can we show they're not consistent with expected utility? So the independence property was stated in a rather complicated notation, independence. Right. So in order to express something in an expected utility, in order for a person's preferences to have the expected utility property, they needed to have continuity and this independence property. The independence property, the definition basically said that whenever I'm dealing with a particular lottery, if I have, suppose that there's some element that's weakly preferred to another element. If I swap a preferred element into this lottery, then if I replace this lottery or any lottery with where I take for one of the states of the world, for one of the outcomes of the lottery, I replace the outcome with a preferred element or another preferred lottery, so then we get to a compound lottery. If I do that, then this new lottery will be preferred. If I replace or weakly preferred, if I replace some element by something better, I make the lottery better. Okay, so what is that? How can we show a violation of that in this case? Well, note that the person is indifferent between A and B, okay? And by the way, the thing that the independence axiom stated about the weak preference relation could be proved to also hold for strict preference and indifference. Pretty simply, we've seen some of these proofs. So, in other words, if I take this lottery and I swap for one of these elements, I swap something in that's just as good as that element, for one of the outcomes that occur with some probability, I swap in for that outcome something that's seen as just as good, then this new lottery should be just as good. So more specifically, I can either swap in, we know that the outcome A and the outcome B are seen as indifferent to one another. Okay, now I know, which by the way means there's weak preference in both directions. Okay, I'm getting fancy there. So I know that this element, that this is indifferent to itself, it's weakly preferred to itself, and as are everything, that's what we call reflexivity. Okay, so if I swap in B here, or I swap in A here, I'm swapping in for some outcome something that the person is indifferent to, which also means there's a weak, if I swap in B here, A is weakly preferred to B, B is weakly preferred to A. So you get the idea of why this will transfer over to the independence of weak preference. But let's just talk about independence with respect to indifference, assuming that this follows from independence of weak preference, okay? If I swap in A over here, okay, then I get this new lottery, 1/2 A and 1/2 A. Okay, I have a half probability of A and a half probability of A. Well, what is that equivalent to? Well, that's just getting A for certain. Okay? So, by independence, if I start with this lottery here, this coin flip between the two children, and I swap in for one of the elements something that's seen as equally good, that then gets me this lottery here, which is the same as this lottery here. I've swapped in something equally good, thus I must be indifferent. So by independence, we should have that this guy, the blue guy, let's call it lottery, I don't know, call it lottery K, must be just as good as this red thing, lottery J. Okay, we'll call this lottery J. So by indifference, if I swap in an A for B or B for A, but here we swapped in A for B, if I swap something in for one of the outcomes that's just as good as that outcome, then I should make the lottery should be no worse and vice versa, therefore you're indifferent. The indifference is preserved when I swap in something that's just as good. So I should have lottery K should be indifferent to lottery J. In other words, half A and half B, I should be indifferent between that and A, but that's violated right here when we said that the parent actually prefers half A and half B to lottery A. Okay, so this preference, strictly as a preference over outcomes, is not consistent with expected utility maximization, with preferences that have to take the expected utility form. However, However, in the example, particularly as it's described with the parent and the children, there's something else going on here, in my opinion. So it's not, this seemed plausible. These preferences initially seemed plausible because we thought, yeah, I can imagine a parent saying, I don't care between either of my children, but I'd rather have a random draw. I'd rather flip a coin than have to choose one or the other, right? But then we're not really just talking about the outcomes of which child has the gift or, is there a probability of each child having the gift? We could say these are really three separate outcomes which have the give gift to A, give gift to B, or toss a fair coin, which have a few different things bundled in it. One is which child gets it. The other is what does the parent do. The other is how do the children perceive the decision of the parent, right? So actually, if I just think of giving a gift to A, call this something else. We'll say GGA. Call this so this is give gift to A. I don't know. So in other words, I'm taking the action of giving the gift to A. So my action, how would you model it? I don't know. My action would be having given 1 unit to the first child, 0 units to the second child, and then also there's the outcome that the first child has 1 unit and the second child has 0 units. And then the second one, give gift to B, I'm taking the action of giving the gift to the second child and the second child has 0 units. And this third thing is some other action that I'm taking. So this could be we'll call this GGA, GGB, and then the third thing is toss a fair coin, TFC. And here I'm doing something else. Maybe these are probabilities that I give it to each child, 1/2, 1/2, and then these are the probabilities that children get it, however we want to notate this. But the point is that GGA, GGB, and TFC could be just 3 completely different things, and there's no problem with a parent saying, I prefer toss fair coin over give gift to A, over which is indifferent to give gift to B, if we realize that these are just 3 distinct things involving not just who ends up with the gift, but what action is taken, what the perceptions of the children might be, etc. So that's why I think this sort of is too easy a rejection of expected utility. This example doesn't really meaningfully illustrate a violation, in my opinion, of expected utility.